Here we have a circuit where we have sequential switching. And by sequential switching, it just means that we have switches that are going to open and close in a sequence, so one after another. How we've been doing this before is we've known that the circuit has been in steady state before the switch is thrown, which tells us the initial value of the inductor current, and then we can use that value as the starting point to look at how the inductor is going to react in the new circuit it's connected to after the switch is thrown. In this case, we're going to have different temporal regions in which this inductor is going to be behaving. The inductor is going to be in one state up until t0, and at t0 you have one switch that's thrown, and the inductor will react to that, and we'll be able to find a current for that inductor during that time. And then at t equal 1 second, we are going to throw one switch and another switch as well. And so in that situation, for t greater than 1, after the second switch has been thrown, the inductor will begin reacting to the new circuit after those switches have been thrown. And so what's going to happen is that the starting point for this second region, or this second interval, is going to be the ending point of this function. So if you know what the function is between 0 and 1, then you can find out what the current is at t equal 1. That's your starting point to allow us to find the current as a function of time in the second interval of the reaction. So the first thing we need to do is to find out what the inductor is doing before t equals 0. And we see here that switch A is closed at t equals 0, so it's open before t equals 0. And so if this switch is open right here, we have a source, but that source is separated by an open switch from the inductor. Switch B doesn't open until t equal 1, so if this switch is closed, then it is shorting out this current source, and essentially all the current through the current source is just going to flow through there forever. This short is going to short out the whole rest of the circuit as well. And so since both of these sources are separated from our inductor, we can say that the current through the inductor at 0 negative before any of the switches are moved is going to be 0, because there's no sources that are connected to that inductor before the first switch moves. Then at t equals 0, we close the switch, and so what we're going to do is investigate this circuit with the switch thrown. Here is the circuit with switch A that's been closed, and switch B remains closed. So as we said before, this closed switch is shorting out this current source, so all of the current from that current source is just going to be flowing around there, so that current source isn't going to contribute anything to the circuit. Since we have this closed switch here, we are shorting out this 9 ohm resistor. The voltage across that 9 ohm resistor is 0 because the two ends are connected just by wire, so this resistor isn't going to contribute anything either. But what we do have that's a little bit tough to see is that we have these resistors, the inductor and the 3 ohm resistor and the 6 ohm resistor. One end of them is all connected by the same wire, and the other end is all connected by wire. So these three are actually in parallel with one another. Whatever voltage we have here that's going to be affecting the inductor, that voltage is going to push current through the 3 ohm resistor and push current through the 6 ohm resistor as well. It doesn't matter that we have a switch here. We can run however much current we want through the 6 ohm resistor, as well as having that current source discharge through that switch. And so what I'm going to do is redraw the circuit, but I'm going to put the inductor out on the end, and I'm going to collapse the other terms together to make this a little bit simpler to see. And so now I want to cut this off here. I have my inductor, and I want to find the Norton equivalent circuit here so that I can figure out what the short circuit current is going to be through this inductor after the switch is thrown. So I see that I have a voltage source in series with a resistor, and then I have a bunch of resistors that are in series and parallel. And so what I'm going to do is use source transformations to simplify the circuit down to a Norton equivalent. And so I took the voltage source and turned it into a current source. I combined these resistors in parallel, and I took the current source and converted it back to a voltage source and combined these resistors. Voltage source converts back to a current source, and I combine the resistors, and I end up with a Norton equivalent circuit for what is connected to my inductor, and this is for t's between 0 seconds and 1 second. So after the first switch is moved and the second has not moved yet. And so I can see here that my equivalent resistance is 1, And so my time constant here is going to be 2. And I can see that my short circuit current is going to be 3 amps. That's coming from the Norton source. Once the inductor starts acting like a short circuit, all of those 3 amps are going to flow through the inductor. And so I can use my starting point before any of the switches are thrown, and I can use the circuit that I have after the first switch moves at t equals 0 to figure out what these values are and to figure out what my current is as a function of time for t being after 0. And so that's going to be the evolution of the inductor until the second switch is thrown at t equal 1, and we'll do a separate calculation there. And so I know my ISC, my short circuit current, is 3. That's from the Norton equivalent circuit connected to my inductor. I know my I0 is the starting current. The starting current is the current at t equals 0, which in this case was 0 because there was nothing connected to it. Then we want to find the inductor current for t is greater than or equal to 1. So what we need to do in that case is look at the same circuit, but when t equal 1, the switches move again. This switch opens up. When this switch opens, it isolates this whole source from our inductor, so this whole part of the circuit won't contribute anything more. It also opens up this switch here, so this current source won't be just feeding back on itself. This current source will now be affecting the rest of the elements connected to it, and so we'll have to do the same thing there. We'll have to investigate this circuit here to figure out what the Norton equivalent circuit is. But if we want to find the current for t greater than or equal to 1, we need to know what the current is at 1 plus, the moment after that switch is thrown. And the way to find that is to find the current at 1 negative, the moment just before that second switch is thrown. And the thing is, we know what the state of the inductor is the instant before that switch is thrown because we already solved for that value over here. And so we can go ahead and plug in I of 1 which is about 1.18 amps. So this is our starting value we found from this other equation, but this is our starting value that we'll use. This will be the I0 for this stage of the current. Then to figure out what the current's going to look like moving forward after this starting point, we have to look at the circuit that we have and come up with the Norton equivalent circuit and plug those values into our equation over here. So the next thing we're going to do is draw this circuit with the switches in their state after t equal 1, and we'll analyze it to find the Norton equivalent circuit. So here we have our circuit after the t is equal to 1. We're looking for the Norton equivalent circuit connected to the terminals that are connected to our inductor. And so if we want the Norton equivalent circuit, what we can do is replace the inductor by a short circuit and find the short circuit current. That's going to be our Norton current. Notice here we just shorted out this 3 ohm resistor, so that's not going to affect anything. What we have are 2 paths. We have a path for our 8 ohm, or for this 8 amps to flow through the 9 ohm resistor and through the 6 ohm resistor. And so what we have is a current division here between these 2 paths. And so we have the equivalent resistance connected to the current source there divided by the 6 ohm resistance is going to give us the current flowing through that 6 ohm resistance. And in fact, it's going to be flowing the opposite direction, so that should be a negative value. Then we need to find the Norton equivalent resistance. So we're going to return to the original circuit. Here we have our Norton circuit. What we want to do is to deactivate the current source and look at the resistance that we have. So we're looking in this way for the equivalent resistance. And what we see there is that we have a 3 ohm resistance in parallel with 6 and 9 ohms in series. And since we have the short circuit current, which is the current from our Norton source, we have the equivalent resistance. We can go back and put in our inductor connected to this Norton equivalent circuit. So now we've figured out what the Norton equivalent circuit is connected to our inductor after t equal 1. And so we know what the initial current is there. The initial current for t greater than 1 is the final current when t equals 1 from the previous interval. We know what the short circuit current is here. The negative value just tells us the direction of the Norton equivalent source, but we defined our current thusly. And so we know that the source is going to be going in the opposite direction from that current, and we have the resistance connected to our inductor. So we can go ahead and find the time constant in this case. We know the currents at the beginning and as t goes to infinity, and so we can plug those in to find our find the current as a function of time. Notice here as well, because we're starting at t equal 1, we have to shift the exponential decay and start it at e to the power of t minus 1, so that we start the exponential decay at the proper point in time. But notice how we did essentially the same thing for the first time interval from 0 to 1, and the same thing from the second interval from t greater than 1. We had to look back to the very beginning to find the steady state before the first interval. Then the end of the first interval was our starting point for the second interval, and then we finished the calculation there. If we plotted both of these, we would see that they're continuous because the inductor current has to be continuous.